Hi everyone, hope you're doing well. I want to pick up where we left off in the in-class lecture talking about electromagnetic spectrum. And we're going to focus right here on infrared. It's kind of in the middle of that spectrum as far as energy is concerned. And in the infrared, remember, we're talking about vibrational modes. Okay, so when atoms are bound to each other, they have a vibrational mode that's loud. We absorb the infrared light, a wavelength that matches a photon with a specific length that matches the gap from ground state to excited state. So if we can put that's H nu, which means light, if we can hit a photon here, we can take that molecule from the ground state to the excited state. Okay? When it does that, it absorbs that particular wavelength of light. So if I shine the whole infrared spectrum on this, okay, and I have a detector back here, I can see which wavelength of light is missing, right? So that's sort of transmission spectrum, or absorption spectrum. So that's what we're basically going to do with this particular form of spectroscopy. Spectroscopy, shining light on a molecular atom. Okay? So let's get into the basics of it. Again, we have atoms that are bound to each other. We also have molecules that have allowed vibrational modes. We'll get into those degrees of freedom and what that means. But as I have a bond vibrating, just like spring, right? It's the exact same kind of thing that we learned in physics with just classical mechanics as far as spring mechanics, Hooke's law. It absorbs a photon, and then it'll go to a higher vibrational mode. Okay, now there's different types of stretching. We can have asymmetric, symmetric, but that's the basic idea. It absorbs that photon of light, okay, and it goes to a higher level. So it goes from ground state to an excited state. Right? And what we get out of that is an absorption spectroscopy. And this is actually written in transmittance, but that's a little different. You'll learn that in 280 lab for sure, the difference between those two. For right now, we just need to say, okay, wherever we see a signal, that's where a molecule absorbs infrared light. And this, remember, is wave number, which is reciprocal wavelength. Oops, not nu, but lambda. Let me find my eraser real quick here. I can't get it. There we go. So this is wave number. And therefore, as we come over to this area, high wave number equals high energy, okay, and high frequency. Okay, this is low energy and low frequency. Okay, so the atoms that are vibrating around here that absorb light are at a lower energy than the ones on the left. Okay, so that's just the basics of the spectrum. We really don't think about it that much. We just report the wave numbers. Right? And the nice thing about these wave numbers is they're going to give us an idea of what functional groups are present. And that's what we're really dealing with here, functional groups. Okay? We can never look at this molecule, at least I can't. Some people can because they can focus on the region down here. But I can't look at that molecule and say, oh, that's definitely methylbenzene or toluene is what this molecule is. Okay? I can't look at that and do that, nor can anybody that I know do that. What we can do is say, okay, this molecule has certain functional groups, and then that gives us at least a class. For instance, I know there's a benzene ring looking at this particular peak right here. Okay? I know there's methyl groups based on these peaks. I know that there's sp2 carbon hydrogen stretches, meaning the hydrogen's off here, by looking at these peaks. And that's what we're going to get good at. Okay, is finding those functional groups in an infrared spectrum. So you can understand if you have an unknown compound, infrared will the only thing it'll give us is what functional groups are present, and really what functional groups aren't present, right? That's just as important. I don't see, and when I look at the spectrum, I don't see an OH stretch. I know what that looks like. I don't see it there. So I can say, well, my unknown molecule is definitely not an alcohol, right? I don't see a C double bond O, so I know it's not a carbonyl. So it allows us to get a sort of a first sort of idea of what functional groups might be present, what kind of molecule we have. The other way we use it is I know I'm making toluene. If I know I'm making toluene, I run the infrared and make sure that infrared matches up with what toluene should look like. Now, the great thing is there are libraries of thousands of molecules. So I can literally say, if I know I have toluene, put it in there, match the spectrum, and it'll say, yes, it's 99% sure it's toluene, okay, based on that particular region down in here as well. So there are some good sort of qualitative ways we use this in organic. Now, most organic chemists will say this is the least used form of spectroscopy. Unfortunately, the ACS on their test thinks it's the most used. So there's a lot of questions on standardized tests from IR. And I think the reason that is because it's a simple spectrum to understand, and we have charts, and it's repeatable, and that molecule gives the same infrared spectrum every time. So it's it's a much easier one to analyze, and that's why I think standardized tests focus on it. But it's definitely not the most used. As a matter of fact, in my 6 years of research and as a grad student, I took probably a handful of IRs in those 6 years. There's some organic groups that just don't even use it. There's other forms of spectroscopy and spectrometry that we're going to learn in this class that are much more sort of informative as far as what the molecule looks like. But that being said, we're going to focus on it because it does have some use in orgo and in organic chemistry, so we'll get it right now. All right, now the spectrum itself, some regions, okay? We're gonna look at, we're talking about identifying function groups, and we want to get an idea where they're going to show up. Okay, so when we look at this, we have OH stretches. Look how broad they are. We'll talk about why. It has to do with hydrogen bonding, but that's a signature OH stretch. Okay, and then we have the region where the carbon hydrogen stretches are. Okay, so these can be sp2 carbon hydrogens. They can be sp3 carbon hydrogens, and they can be sp carbon hydrogens. Okay, so what does that mean? That means a carbon that is sp3 hybridized, like in a tetrahedron, is going to give a certain signal. Okay, and we're going to have sort of cutoffs all around this region where each one of those represents or shows up. Okay, so when I look at that region, I can say, okay, I think I have sp3 carbon hydrogens only, or I see some sp2 carbon hydrogens, so that means I have double bonds present. So it really gives us some information right here, and that's the carbon hydrogen stretches. So that bond, depending on its hybridization of carbon, absorbs at a different wave number. Okay, then we have the Orgo-2 classic. You'll get sick of this in Orgo-2 because most of Orgo-2 deals with carbonyls, right? So the entire class is pretty much carbonyl chemistry. So you're going to see this a lot as far as an IR peak. So when I see that right around 1700 or 1600, it's actually 1700 reciprocal centimeters. That's where you write that. That's wave number. We get an idea. We put the wavelength in centimeters. That's why you see the centimeter. And then it's 1/, so it's reciprocal centimeters. So that's a great CO stretch. So if I see that in an IR spectrum, I can pretty much be assured I have a carbon double bonded to oxygen. The CC stretch comes around 1500 to 1600. And we're going to have charts for all this, so you don't have to worry about it right now. I'm just showing you, what by the end of this, you want to know where these are so that you don't have to keep looking at charts for certain things. Then we have a CO stretch. So if I have an alcohol, that's different than an OH. The O is bound to the H. That bond absorbed, vibrational modes absorb around 3500. This bond, the CO, right, if this is the alcohol, it's this bond I'm concerned about, is right around 1200. So those are the ones that we focus on. This rest of this region, and I'm pretty much of the school, anything below 1200. Okay, so 1200, and so that'd be less than 1200. Okay, reciprocal centimeters is called the fingerprint region. Now the reason they call it a fingerprint region is because every molecule has a unique fingerprint region. So technically, I could identify the molecule, if it's an unknown, by the fingerprint region. And there are libraries that help us do that. The problem is they come back with, well, it's 85% chance is this, there's a 15% chance is this, there's a 5, so it's really not an absolute measurement, but it really is close. And with the advent of software that really does some high-level deconvolution of these, we can get a pretty good idea what molecule we have. Now, the problem is it's a library of about 30,000, maybe more now, 100,000 compounds, and you pay for that. Trust me, you pay a lot of money for that knowledge. But it's limited, right? Because if you're making unknown, or if you're extracting unknown molecules from natural products, there's a high chance that molecule you're looking at or looking for is not part of that library. So most organic chemists don't rely on it. We have other methods like NMR that are much more valuable, and mass spec, to what the molecule's identity could be. But for purposes, that fingerprint region is there. The people that can analyze molecules by fingerprint region without computer help really can't communicate to normal people. They're a unique brand of analytical chemists. Okay, so regions, the same slide, just a little bit different. This may be how your textbook presents it. And this is what I want to remember. This is what I want to memorize, is where these things roughly show up. So I know where to look. And then I can go to charts and figure out what type of CH bond it is. Okay? Or I can go to charts and figure out what type of CO bond it is. Remember, you have different functional groups. You have ketones, aldehydes, esters, amides, anhydrides. You'll see two of those peaks there. So a lot of difference in what these things are, and we have some that are, bound to aromatic. That changes it too. So we have charts that really help us out on what type of C double bond O it could be. Okay? And again, I wouldn't memorize any of those. What I would memorize is roughly where these things show up. So standardized tests won't give you charts. I'll always give you a chart. That's why charts were invented, so we can look them up. I guarantee every organic chemist that's doing work with carbonyls will go to a chart to look up exactly what region it is, because there's just too many different types of carbonyls. But you want to know where these rough sort of areas are, and we kind of ignore the fingerprint region. We don't look at anything down there. We're looking at functional group. We call this the functional group region. Okay? That's what a machine looks like. The IR happens right in there. It's just a little sort of window for the light to shine in. What we use salt plates that are sort of round like this, and they're about that big actually compared to the screen. And these salt plates, we put them together sort of we put the sample in between there, neat, meaning pure. If it's a liquid, if it's solid, we got issues. We got to make KBR pellets. It's really pain. And then we put those two plates together. The reason we use salt, KBR salt, is because that's inactive in IR. It's not. It's an ionic compound which doesn't have the bonding vibrational modes in the region that we're looking at. So our sample holder is inactive. The problem with students is we'll get these salt plates, we'll use them, and then they'll go to clean them. And remember, in organic chemistry, we like to use acetone to clean things, which is what you need to use here. If people use water, they're gone, right? The KBR plates will dissolve. So we always have to make sure we use an acetone. The problem is acetone is this, and it has a carbonyl in it. So we can get false carbonyls because of the cleaning solution, this acetone we use. So the actual technique is something we might do in Orgo 2 for you. But if you joined a group, they could teach you how to use this machine in probably 10 minutes. The software is ChemStation software is really easy. Machine costs about $35,000, right around there, and that's all software, right? The optics of this are pretty cheap. I imagine this machine is probably $5,000, maybe even less for just this part of it. It's the software package that integrates the computer in with all of the library and all that stuff. That's what costs tens of thousands of dollars. Okay. Now let's get back to infrared spectroscopy and what gives a signal. And it's really the separation of charge. Okay. Dipole moments. You're going to hear that quite a bit. So molecules that have dipole moments are going to be IR active. Okay. Molecules that don't are going to be inactive. Now, when molecules said to be IR inactive, it's because it's symmetrical, like carbon dioxide. That's considered IR inactive, except for a few asymmetric stretches. Meaning, if I'm just talking about the bond between here and the whole overall molecule, it doesn't show an IR signal, because when it increases vibrational modes, they're both going in opposite directions, and I don't change that center of gravity or dipole moment. That's what I think of a dipole moment, is a center of gravity. This is a non-polar molecule, and that's what we always want to keep in check. So that the whole polar versus non-polar in Gen Chem really pays dividends when you're doing something like this, because I can look at a molecule and say, okay, CO2 is non-polar. It should be IR inactive, because there's no dipole moment, which is called mu. Okay? If it doesn't have a dipole moment, it's going to be IR inactive, except for a few stretches where vibrational modes where the molecule could do this. So I'll just kind of draw it here, where this stretch could go here and this one goes here, right? That's an asymmetric stretch. And that vibrational mode, which is allowed, it will allow it to absorb some infrared light, but it'll be very weak signal, and it'll be down in the fingerprint region. So we really kind of ignore that. So we really just think of these as IR inactive. Okay, so that's what the basis for a signal is. It has to be a molecule that has some polarity or dipole moment. Okay, so we can look at HCl versus Cl2. And we can see that an HCl has a dipole moment based on electronegativity differences of the H and the Cl of 3.3 times 10 to the -3 coulombs per meter, or Dubais, right? So that's 1 Dubais is equal to that. So a 10 Dubais charge separation is basically a +1 -1 charge separated by 1 angstrom. This is stuff you're going to learn in, let's say, analytical chem class. Dr. Hinsey, some of you had him for Gen Chem. He'll teach a class, and it's instrumental analysis class, and you'll go through all of these sort of calculations and being able to understand exactly where each cell is going to show up. Right now, we don't need to know that. We need to know that there has to be a mu, a dipole moment, to have a IR spectrum. Okay. The types of vibrational modes that are available for these molecules depends on the number of atoms. So if the more complicated the molecule, the more signals I'm going to get, the more chances of different allowed vibrational modes that are available. So you get these things called degrees of freedom. And again, this is analytical chemistry. Too much math for us organickers. Okay, we know that if a molecule has a lot of bonds, it's going to have a lot of signals. That's kind of the mindset that we take. I don't think any standardized test is going to quiz you on available degrees of freedom, available vibrational modes. But who knows? I'm not the one testing you in the end. So you kind of want to read through it and understand it, I think, is the most important part, as opposed to memorizing all these formulas. Okay. Now, the types of vibrational stretches you see. So these are stretches, meaning that we have different. If we have a 3-atom system, we can kind of do these. Where the molecules go back and forth stretch. We have asymmetric stretches, and that's really what I was showing you before. And I wish I was in person, because I showed you with my arms, and I will the next time we're in class. Actually, I did a little bit in the in-person last class, but I'll kind of go through some of these, and you can think about the 3 atoms sort of like this. So if this is the vibrational mode, you can imagine that bond getting longer and this bond getting shorter, and then this bond getting longer and this bond getting shorter. That's an asymmetric stretch. A symmetric stretch would be where they both increase in length the same amount. So that one would get longer and that one would get longer, right? That's a bad example. They're pretty much close, same size. Let me go back and do that one again. Where is my eraser? There we go. So there's sort of, this is going back and forth, and then it would get much longer, right? That's the change in that, and that's an asymmetric, because the mu, or the dipole moment, doesn't change in that type of stretch when it does those vibrational modes. It has a mu to start with, so that's why it's active. Now there's a lot of bends, and these are actually technical terms: scissoring, wagging, back rocking, twisting, torsion. Right? Those are all different types of bends that occur. Most of these are down close to the fingerprint region, or at least they have a very low intensity to their signals. So we kind of ignore some of these, but if you're truly into infrared spectroscopy, you'll find these stretches, and these bends will make sense. But for us, we're looking at a very simple system. We're going to look for these functional groups, right? The ones I just mentioned there, we're going to look for those. And we don't care if they're bending or stretching or whatever. We're just looking for those bonds and those types of functional groups that are present. So we're going to make it a lot easier than infrared spectra actually is. Okay. And again, this is just showing you for CO2. Most of it is a symmetrical stretch. Those are most of the stretch, and those are inactive. But if I have an asymmetric stretch for a molecule that is nonpolar, I will get a signal. It'll be weak though, and so we really ignore that. So we don't use nonpolar molecules in IR very often. Now we can look at some hydrocarbons and look and see they're all sp3 carbon hydrogens, because you'll see some stretches there, but that's still something we don't usually use. Okay, we're looking for functional groups, and specifically we look for C double bond O's, COHs, right, and double bonds, maybe in some aromatic compounds. We look for those functional groups by IR, and that's usually what organic chemists use it for, to find these functional groups if they're present, or to see one disappear. If I'm doing a reaction and I'm taking a carbonyl to an alcohol, I can watch the carbonyl signal go away as I make alcohol, right, and I can see the OH stretch show up. Okay. So signal strength can vary, and that helps us identify what functional groups are there. So we have strong signals and weak signals. You also see some medium signals. Also, people call that an intense signal as well as a strong signal. But that really, is indicative of the type of functional group, because certain functional groups that are more polar absorb more light. Okay, that's really what we're talking about. So you take a polar bond like carbon double bonded oxygen versus carbon-carbon double bond, which has very little polarity difference. And you can see that as this bond stretches, it's better at absorbing light. This bond doesn't stretch as much because the electron density isn't changing that much in that stretch, right? It's more of a a non-polar type bond, so you don't get that big dipole moment change, and therefore it doesn't absorb infrared light very well. So some molecules, this is polar the way it's bound there because it's asymmetrical. You'll just see a weak signal, but other functional groups you'll see a strong signal. Okay? So that's really the difference in the intensity. It has nothing to do with the light source shining on it. It has to do with the type of bond, and the greater the polarity, the stronger the IR signal. And that's what you want to take from this. Okay, so if we look at these two IR spectrums, right around 1700, I know I have a carbonyl. I don't know what type of carbonyl it is. I have to go to charts, and I can see that the C double bond C is around 1600. So it's roughly the same energy that it absorbs as far as wave numbers, but is a much weaker signal. And that really helps me distinguish between a spectrum that has both functional groups there. Okay, or just one or the other. I can say, okay, it's a weak signal compared to on the spectrum, therefore it's likely a C double bond C. Especially when you're getting into this region right here, right? If it absorbs right here, is it a weak signal or a strong signal? If it's a weak signal, I think it's a carbon-carbon double bond. If it's a very strong signal, I think it's a carbonyl. Okay, so that's really important, that the strength of the signal that we observe. Okay, we'll stop there, and I'll pick up with how to analyze an IR spectrum in the second part of this lecture.